World Lines, a quantum supercomputer poem by Amy Catanzano. When we think as far as our world lines, our thoughts become movements. In space, motions knotting intricate path like strands of DNA intertwined. The mind of particles traveling as their orbits in space-time, not particles. Of indefinite location, the world mind is a record that orbits its knotted history. Computes qubits, its world lines, the braided motions of mind's memory. All right, so with that poem, that was a poem by a poet slash, I would say, science aficionado. And in case you had trouble understanding how I read that, for every white word, you can either decide to go up or down. In other words, the green and the blue or teal are entangled. So this entire poem is, you get choices and they're all knotted together. Which leads to actually the topic of this episode. Now, what are you listening to, first of all? This is SG2 on Space, the only weekly space show in Houston, Texas, as well as probably the only weekly one in the state of Texas. Be sure to follow me at facebook.com/The Shen Show. You can also find me online. Go on YouTube, look up Action One Media, or look up actually SG2 on Space, and you will see a list of all the episodes. We're live every Wednesday night, 6:30 p.m. U.S. Central, except maybe not next week because it's Thanksgiving. But aside from holidays. And be sure to support me at patreon.com, patreon.com/SG2 on Space. That would be greatly appreciated. In any case, why don't we get the show started? So today, quantum entanglement. That's something I constantly bring up and wonder what the heck that is. And the Leonard Kramer over there, Dr. Kramer, was someone who suggested that he just loves spewing out that word. So I figured we would take some time and spend an episode talking about what exactly quantum entanglement is. Now, I understand that we talk about quantum mechanics a lot, but this is specifically focused on this aspect. So it's a very weird part of quantum mechanics. Now, so Leonard, you like to throw out that word.
Yeah.
So what exactly in your definition, what is it? I guess that's a pretty broad question.
It's two particles that are governed by the same state wave function in quantum mechanics, and they can be separated by an arbitrary distance. One can be on one side of the universe and the other on the other side, and yet they still are governed by the same wave function.
I think before we dive deeper into this, maybe we can play a short little video if we can get it there. That briefly summarizes it whenever we get there. So this there you go.
Get entangled, which is what scientists call the quantum entanglement of electrons.
Yeah.
Once the electrons are entangled, the two electrons can only have opposite spins. That is, if one is measured to have upspin, the second immediately becomes downspin. Now, we know that the two electrons, unmeasured, do not have a single spin, but a superposition of both up and down spin. If we were to separate the two electrons arbitrarily far, say, we put one in a physics lab on Earth and another in a different lab somewhere in the Andromeda galaxy, and we measure the spin of the electron on Earth, we will immediately know the measurement of the one in the Andromeda galaxy. For example, if we measure the Earth electron to have upspin, we immediately know that the other electron has downspin. This information traveled instantaneously, faster than the speed of light. As one can imagine, this idea greatly bothered famous physicist Albert Einstein. It was such a disturbing realization, in fact, that he called this phenomenon spooky action at a distance. So how can this spooky action at a distance be useful to us?
Okay.
Well,
all right. I think we can pause here. So I think that cartoon presented that particular case, but then gave something else which might confuse some people who view it. So you mentioned the important word of superposition. Leonard, what exactly is superposition, and how is it important in quantum mechanics?
Well, the superposition is merely the realization that if you have multiple states for a measurement, that the actual state at a before measurement is sort of composed of all of the possibilities all together. So some of you may have heard about the Schrodinger cat being in a superposition of being both asleep and awake at the same time. Of course, that was used by Schrodinger to show the absurdity of that notion for a macroscopic system. So that's what superposition is.
So in other words, like for instance, let's pretend this is like say electron spin. Okay.
Yeah.
Now, classically, in classical mechanics, we will say, okay, we know for sure it's like this, but quantum mechanically, it's not. It could be there's a probability it's like this or like this, and that's what it was showing in that cartoon. Essentially, that it is a combined. It's like it's every single possibility. In this case, there's only two possibilities combined.
For the two together, with the two particles, the two electrons in that example, then if when they're together, it's a superposition of either one of those states. Now, one of the things is that what you measure is utterly random. You will measure either up or you will measure down, right, or left or right, depending on your choice of direction. So it's a very mysterious, very strange thing about particles that have spin, but there's other things like polarization and position and all those kind of things that we can talk about also. But in this example, it's this spin. What is spin? Spin's a kind of angular momentum, but never mind. It's just a thing, like mass or charge or whatever that's applied. That is an attribute of the electron in this case. Doesn't or the particle. So it's a random number. Now, okay, well, go ahead. I mean, did I answer the question?
Well, yeah, I think you did. I mean, it's random in the sense that you don't know what you're going to measure when you measure it, but it actually does follow a certain probability with the whatever.
There are probabilities and distributions to probabilities that are associated with various quantum phenomenon. For the spin, it's either or with equal probability.
Right. That one.
Yeah.
Okay. No, that makes sense. Now, Einstein had a huge issue with that because what did he say? Spooky action at a distance. As the cartoon depicted, you could literally have these two, if they're entangled, like way out in the distance, Andromeda galaxy, say. You observe one, instantly you know what the other one is. How do scientists know how that's possible? Because that seems to defy, the speed of light limit.
Yeah. Well, that was what disturbed Einstein, and in the 30s, he wrote a paper with two other authors, and it's known by the initials Einstein, Rosen, and Podolsky. And this is a famous paper where this was supposed to prove that there was something deeply incomplete about quantum mechanics. He says there's hidden variables because of this phenomenon, but things proceeded for several decades until the early 70s and about 1981, when definitive measurements were made that demonstrated that he was wrong. That in fact, this phenomenon actually does transmit a certain kind of information instantaneously, and we've been trying to figure out what it means for the ontology of the universe, since then. And I actually have some personal ideas about that, but
we'll talk about that in a little bit. Now, do you know how two particles become entangled? Does it just happen? Okay.
Yes, this is a common kind of thing that happens. So suppose I have radioactive decay of something with a spin 0. So there's particles that have spin 0, which means they have no angular momentum, and they will decay into two different particles, like two electrons or an electron, and each one will have an opposite spin, so that the total angular momentum remains the same, but the two particles have separate spins. So that's how that happens. You can have photons that are produced with opposite polarization, or orthogonal polarization, and that sort of thing. So
I think I get it. So
yeah.
the originator, so to speak, whatever phenomenon originates it, is somehow neutral, let's just say. And when it splits into two particles or whatever, they are entangled together because summed together they have to equal whatever the original property is.
Exactly. Now, I think we should talk about your socks.
Okay. Wow,
so
they're not even human.
Right. So if you took those two socks, this is a confusing kind of thing. You took the two socks and put them in a bag or something, and then you gave me one of your socks, and I went and looked at it, and it was the one with the, what is it, a Mickey Mouse or something on there?
No,
okay.
It's a tiger.
Okay, tiger. It has the tiger on it. Then I would know you had the black one. You had the one
Yep,
without.
I have the black one. Yep.
Yeah. Yeah. Okay. So big deal, And when I first heard about this in graduate school, I was thinking, well, I mean, there's nothing mysterious or strange about that, but that's not what's going on here. The analogy with entanglement, the analogy is more like magic dice, like two dice, and that these dice, no matter which way I roll them, no matter how I roll them, I always get 7. So if one of them's a 5, the other one will be a 2. If I look at, if I roll it, and one will be a 3 and a 4. 3 and 4 is 7, right? 3 and 4, yeah. So
yeah.
So or a 5 and a 1, right? So it's magic dice like that. So that if I were to mix up the dice and I were to give you one, and you were to look at one face, then you would immediately know what the face is of the one that I have, even though you don't know which face I'm looking at, So it's like both give a random number or a random event that are remote from each other, very far apart, but they're absolutely correlated. And you don't know that until we come together with our record, Well, you rolled a 5 and I rolled a 1. You rolled a 3, then I rolled a 4. Right. So you would know that, but you wouldn't know what the answer was. So there was so that's why that's the actual analogy that we should be looking at. And the way sorry.
No. I was thinking, I mean, that's a lot more magical, because then from a everyday perspective, it doesn't make sense. Like the sock one, then it's like, yeah, for sure, whatever. That's so,
Right.
Now I have a question though. You said I have to observe it. Now, does that mean that if you observe yours, let's just say you observe your dice to be 3, and let's just say it has to add up to 7, they're entangled in that way. That means the next time I observe it, when I observe it, it's going to have to show up to be 4 somehow.
Yes, somehow, yes.
Now, if we both observe it at the same exact time somehow, how does that work?
That's the fundamental mystery. And we could be on we could be up on different planets, and the same thing would be happening.
So let's just say you and I observe at the same time. It's still going to instantaneously show up, and they're going to sum up to be, like in this case, 7.
And that's a fundamental strangeness that and Einstein was aware of this, and he objected to that. So, but it was proved in the early 80s. There's the researcher's name is Aspe. It reads in English like aspect. I don't know. So this is a fundamental mystery that simply has blown physics away. So we don't. It has some applications for things like cryptography and unhackable messaging and that sort of thing. Outside of that,
Well, look, one of the things that you and I talked about shortly before we started the program actually was on Hawking radiation, which is rather interesting. About how a black hole, and I think we mentioned this before in previous episodes, about how a black hole actually eventually disappears due to radiation that's emitted, and that's somehow related to quantum entanglement. Can you explain a bit about that?
Sure. The way I understand it, there's a couple of different ways to understand Hawking radiation. And backing up, Hawking radiation has to do with this theoretical demonstration or theoretical explanation of the way black holes will evaporate that Stephen Hawking's came up with in the mid 70s. So what happens is that there's two ways to look at it. You can have a wavelength of a vibration or some radiation inside the black hole that's of the same order as the dimensions, as the width of the black hole and the particle being tunneled out. But that's also equivalent to virtual particles that are being produced in space all the time that are entangled. And at the point where the event horizon, that's the point of no return, where if you go inside, you can't escape. At the event horizon, the two particles are created. One is inside, or one drifts inside, and the other one drifts outside. And so that particle then is lost and is emitted as radiation. And generally, we think it's actually a photon, or it's some gravitational effect that's emitted, and the black hole will lose mass and gradually lose.
Eventually, it will disappear. Yeah. You mentioned virtual particles. From what I understand, those are like really transient, like they appear and they disappear in like a fraction of a second, and they always appear in pairs. Is that correct?
This is happening all the time in space. It's a
and it's due to it's due to the fact that there's such a thing called a quantum vacuum, which we're not going to go into here. But point is, the quantum vacuum actually has some inherent like energy, I believe, and there's some fluctuation, and so these particles are constantly appearing and then disappearing. So, but in any case, when it's near a black hole, though, one of the particles, they cannot. I think, from what I understand, these virtual particles, they typically, do they collide with each other? Is that why they disappear?
And, well, the vacuum will just borrow some energy from the future, or
okay,
and then it gives it back, in the present, and so it'll create these particles that are just there. It's like the vacuum has a soup of these particles that are being generated constantly. So
now,
and you have to understand that we're right at the bleeding edge of understanding about physics, and we're also kind of beyond the point of measurement or observation. So all of these things are, one of the frustrating things is that we think that we're only thinking about these things. We really don't know how to make measurements of these things. So it's we're just in theoretical land. But
well, I know it has been demonstrated in labs that this literally actually does happen. These quantum.
The entanglement is certainly is certainly, but the mechanisms for black hole physics are still
got it.
Is what I'm saying, is unobserved. So and we don't really have any prospect of I don't think ever observing these things. So.
We should talk about that next time. Black holes. Just a thought.
Okay.
Now, okay, good. Topic for next time. So let's see here. What was I gonna say? You said you had your own theories. Remember that
Yeah.
a few minutes ago? What are
Well,
they?
this notion that when you roll the dice, or when I roll the dice, I see a number there, and I know exactly what you're going to roll on the other side of the universe, right? Well, one way to resolve that is if the that event is already predetermined. In other words, it already exists in a certain sense, and that so this is a concept called superdeterminism,
Mm-hmm.
which means that all of history. Okay, imagine all of history from the past, when history began, to the end of history, is already exists in some respect, and that we're just following a path through it that takes us from one point in time to the next, and all of the events that are going to happen will happen and are predetermined um, before they've happened. And so that this would explain the phenomenon. I'm not saying that I'm right, but that's a very elegant uh, explanation for actually all of the non-determinism, all of the probabilistic aspects of quantum mechanics and a lot of the mysteries. I don't. It's not necessarily so useful because I don't know how to
Mm-hmm.
predict it, or how to, but what if you just allow your mind to become, just think about it in that respect. um you, it seems like a very compelling way of explaining the all of the phenomenon, all of the issues that have to do with quantum mechanics, which is that we see nature produces random numbers, and that's what you don't hear about a lot.
Mm-hmm.
When we're learning quantum mechanics, we're just learning how to calculate these things, enormously successful, but we don't understand the ontology, the underlying machinery that's going on. And but if super determinism is the ontology, that the history has already been determined, and it's only our role is to be on the roller coaster and follow the path that it's taking us, then it becomes clear. We don't understand anything else about it, but that would be that is kind of my favorite explanation for how that works. And um, so the
I mean,
that
this will mean that there's no. This leads back to what we talked about, I think, last week on free will.
oh oh
Uh,
yeah, huh? What do you
so
know?
according to this, then
What a
there is no free
coincidence.
will. What a coincidence, indeed. So if we allow the prospect of having no free will and everything's determined since the Big Bang, then that's super determinism. We will not have this confusion on why there's probabilities and why it has to this entanglement
Hmm.
paradox
Yeah,
um,
the
confusion.
biggest
Hmm.
problem I see with quantum mechanics is the random numbers. Right now, if you're into computers and simulations and things like that, random numbers are not easy to come by when you write a deterministic computer program. It's a that's there's a certain art to getting the random
Hmm.
number. So what is nature's random number generator? I haven't seen anybody. I I I'm curious about that. I'd be interested in an agenda where scientists inquired into whether the numbers that we're getting out of a random event truly are random, or what are the characteristics? Are there some correlations, or maybe there's some smart people that could examine those things, and that would get us back to some of our intuitive ideas about free will and so forth. I know that I'll mention Roger Penrose because I know our time's getting short here. Roger Penrose is aware of these things, and that's why he's looking for the microtubules and stuff that we talked about last time. So,
no, I mean that is, as I was telling you, I myself do not happen to agree with the fact that we don't have free will, but
well,
who knows?
I wouldn't choose it if I could, but.
Yeah, who knows? We're gonna have to definitely investigate this, and there's a lot of people looking into this right now for sure. For now, though, we got to turn to something more bizarre. Let's just say. So,
UFOs.
yes, why not? Like that is stuff that you see up there, right? I mean, you can't see quantum particles, but you can definitely see these UFOs. Who knows? Maybe they're using entanglement somehow.
Mm-hmm.
So, in any case. What is going on with the world of UFOs? Well, look at this little picture. Leonard, do you know what this is? What do you think that is?
Looks like I don't know. Looks like something. Looks like something. I don't know.
Okay. Yes, it does look like something. I don't know why all these photos of UFOs typically are really fuzzy. I guess people don't have their cameras ready all the time. But
maybe
so
there could
so
be
this guy
a clue.
This was
Pictures
taken
of
back
Bigfoot
on.
are like that too.
Yeah, I know. 45-year-old pilot Charles Cobb. He apparently took this picture in late October in North Carolina, and it was this. He actually took this in June, but I guess the story didn't break out until recently. So the object was round, irregular, as you saw in the photo, and essentially this guy is an 88-year-old Korean War combat veteran,
No, I'm not gonna mess with him.
Yes, don't, even though he's 88.
Yeah.
So he pulled out this was taken northeast of Asheville, which is a pretty popular tourist destination. Actually, I've been there last December, that area, just coincidentally. Cobb said he took out his iPad and took photos of this flying object in its opaque center. This was on June 12th, 11:18 a.m. And he recalled the craft dropping at times to maybe 15,000 feet before shooting back up to at least 30,000 feet. The object vanished at one point when he was looking down his iPad, but then soon it reappeared. So it could zoom up almost out of sight, and it was also flying parallel during the 15-20 minutes you watched it. So it could not have been a comet. So definitely not a comet. And there's no other reported astronomical object that appears in the sky on June 12th, 2020. And there's no, the shape of the object does not match that of any airplane. And it was, there's, anyways, so he was also saying the object, while zooming to incredible heights and coming back down, was always heading in north direction, yet it remains in the general area that he was viewing. So a plane of any sort would have passed through his viewing area and would have been out of sight in a few minutes. And he shared those with some pilot friends, and they are quite stumped as well, and nobody knows what exactly it is. Apparently in that area, there's quite a lot of UFO sightings. So that's rather interesting.
You need special glasses to see them, shot glasses.
I have no idea. Yeah. So Charlotte, North Carolina is one of the top 10 largest North American cities for the total number of UFO sightings in the past century, apparently. So
that's interesting.
That is. Now, this kind of thing is not limited to just like one or two people seeing. Apparently, back in 2003, there's also cases of UFOs appearing with for instance, I just give you this example. In 2003, there was an airline pilot who was the plane was going from Dallas Fort Worth to Charlotte, and the pilot saw a mysterious object that came within 100 feet below him on this commercial flight, and there were nearly 100 passengers on board. The pilot had to maneuver to avoid this unknown object.
When was that?
So
That was like
this was back in 2003. This was on flight from Dallas Fort Worth to Charlotte, and I think there's a YouTube video showing this, but yeah, it's pretty crazy. Anyways, so History Channel, the History Channel actually recently created. I think they have a show or some episodes now on like unidentified flying objects, and airplanes actually on that. So the entire UFO investigations. So, anyways,
yeah.
all right,
I have an open mind about it.
I'm done mumbling, not mumbling, bumbling. I don't know, whatever. Talking about this.
You're doing well.
I'm still waiting for the sometime when I look up. Let's see. Speaking of which, look up because you never know what you'll see, right?
Yeah, I always do.
What do you see?
Your
ceiling?
The ceiling is everything's fine in here. Yeah.
Okay, wonderful. But for those of us,
dusted,
those of us who want to go outside some point, look up because you never know what you'll see. Leonard, thank you for being on the show again.
Wait. I saw the space station last night from Houston.
You did?
And it was followed by SpaceX. I just want to say that. I know we're out of time. Sorry. I did.
No, that's really cool. Probably.
And one of the astronauts is a classmate of mine from grad school named Shannon Walker. Anyway, she's up there.
That is wonderful. Yeah, I'm so glad that commercial space is doing this. Yes, guys, even if you don't see an alien or UFO, you could definitely catch things like the International Space Station. In fact, it's pretty easy to see. You just need to look it up, figure out where its trajectory is, and look up at the appropriate time. You will see it. Okay. So with that, we're going to have to close. Thank you, everybody. So follow me, facebook.com/The Shen Show. Where go on YouTube, subscribe to the the playlist with the SGT on Space. Support me, patreon.com/SGT on Space. And we will, one last important thing. Leonard, are you going to be here next week?
Next week? I can do a show next week if you want to. No, Thursday is Thanksgiving.
Yeah, I'm wondering if you were traveling or whatever. But if not, we could do it.
I'll probably be traveling that weekend, but going up to Dallas to see my son. But no, Wednesday, let's do it. Okay, the 25th then, we're still going to do the show. So we are going to be talking about, we said black holes. So let's talk about that. Okay, they're pretty interesting. They are. I don't think we've talked about them before. I think we have. So, we have? I think so, but let's talk about them again. Sure, why not? There's new discoveries. Yeah. What the heck? All right, everybody. Have a good Wednesday night, and we'll catch you next week for the live show. So, namaste.